Very good morning. Welcome to the fifth week lectures of Applied Multivariate Statistical Modeling. In this week, we primarily discuss on multivariate inferential statistics. Today we cover the basics and modeling t-square statistics. We start with multivariate central limit theorem followed by modeling t-square distribution, then one example, and then we give the concept of confidence region. Whatever we have learned in the univariate statistics, but in the domain of inferential statistics, those concepts are equally applicable here. But as the treatment is in the multivariate domain, so you will learn that what way the univariate theories will be converted to the multivariate domain. That is the crux of the matter, and I hope that you will enjoy the lectures. Let us see the next.
Now let us think that you are sampling from multivariate normal distribution, that X is multivariate normal where the population parameters are mu, which is mu1, mu2, it is a mu vector p cross 1, and your covariance matrix is p cross p, and you all know that what is the elements, that is sigma 1 1, sigma 1 2, like sigma 1 p, sigma 1 2, sigma 2 2, sigma 2 p, like this, sigma 1 p, sigma 2 p, sigma p p. This is what is your population. When you sample from the population, for example a sample of size n, then you compute sample statistics like x bar, which is again a p variable vector, x1 bar, x2 bar, like this, xp bar, and you also compute that covariance matrix, which is S11, S12, S1p, S12, S22, like S2p, and followed by this S1p, S2p, dot 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 SPP, p cross p. What formula you have used earlier? You have seen already, you have seen that you have used this formula to calculate this. If your data matrix is A x n cross p, then what you have used here, you have used this one is 1 by n, then x transpose, and you are creating a unit vector here, where 1 is 1 1 1, like this, 1 n cross 1. For sample covariance, you have computed like this, that is x minus your, it will be p cross p. So, 1 dot x bar transpose, then transpose followed by x minus 1 dot x bar transpose. This is the formula you have used. Fine. Now, when we talk about the inferential statistics, you have seen in univariate case also that we talk about the distribution of the statistic of interest. For example, you may be interested to know what is the distribution of x bar. Similarly, what is the distribution of S? Now, x bar that follows normal distribution, that is multivariate normal with p variables mu sigma by n, and S follows Wishart distribution, with n minus 1 degrees of freedom. This is a complex distribution, Wisher distribution. We will not talk anything about this Wisher distribution henceforth. Okay. Now, then the another issue what you have seen in the univariate case also, that is central limit theorem. Now, central limit theorem for multivariate data, for multivariate random variable x bar, what will be this? Here you have seen that square root of x bar minus mu, that follows multivariate normal with 0, mean vector 0 and that covariance metric sigma. Last class you have seen, some of you have seen, not all, this one, and also we have seen that in x bar minus mu transpose S inverse x bar minus mu, this follows your chi-square distribution. That is what multivariate CLT, multivariate central limit theorem, multivariate central limit theorem. This second part, that in x bar minus mu, S inverse x bar minus mu, that follows chi-square distribution provided n minus p greater than equal to 40, large sample, that is large sample. Okay. Now, what will happen when your sample size is small? So, you go for small sample. Small sample here we are saying that n minus p less than 40. This I have seen in the book by Young and one more professor is there, that applied multivariate modeling in quality management. This is the what I can say when you say it is small sample less than equal to 40. Okay. Now, let us see how do we develop this one, the distribution for the required statistics for x bar when your sample size is small. What we have seen earlier, that in univariate case, when your sample size is small, you have used T distribution, T equal to x bar minus mu by S by root n. This x bar is the mean, sample mean, and mu is the population mean, S is sample standard deviation, n is the sample size. Now, I want to see what will be its multivariate counterpart. X bar will no longer be your scalar quantity, it will be x bar. Mu also will be a vector quantity, and S will be replaced by that this S, and n will be remain n. That is the case. Okay. If you rewrite this, what you will write, that T equal to x bar minus mu, then here we write square root of n, then S to the power minus 1. Okay. Now, if you make T square, what you will get? N x bar minus mu S square to the power minus 1 x bar minus mu. Now, we like the multivariate normal distribution we developed using univariate normal distribution. Here also we will use the same formulation, similar formulation. So, instead of this t square we will write capital T square, which is known as Hotelling T square. Hotelling's T square. So, this will be written like this: n x bar minus mu transpose, then this will become a s. So, what we say here that s, that counterpart will be taking at capital S, basically this is a square in terms of variance. So, S inverse x bar minus mu, and Hotelling has proved that this quantity will follow n minus 1 p by n minus p f p n minus p, that is f distribution. It will follow f distribution. So, when you take small sample size, you will find that this is the statistics. This statistic is of importance now, and the derivation of this t square is this, and it will follow this distribution. Okay. Now, see the problem what I have solved in another class. Again I want to solve it here, and it may be repetition for some of you, but for others it is not that. So, a random sample with size n equal to 20 were collected from a bivariate normal process. The sample mean vector and covariance matrix are given below. What is this? X bar is 10, 20, that is the mean vector, and covariance matrix is S, that is 40, minus 50, minus 50 and 100. We want what will be the value of Hotelling T square, that statistic value. Answer is this 1.33 10 minus mu 1 to the power square, like this. So, for some of you who are not gone through that computation, for you please see what is this t square is n x bar minus mu transpose S inverse x bar minus mu. What is your x bar? X bar given 10, 20. What is your mu? Mu is mu 1 and mu 2, because it is a bivariate case. What is S given? S given 40, minus 50, minus 50, 100. What you require to compute? You require to compute first x bar minus mu, which is 10, 20 minus mu 1, mu 2. This is nothing but 10 minus mu 1, 20 minus mu 2, which will be a 2 cross 1 vector. Then you require to compute S inverse. S inverse is 1 by determinant of S adjoint of S. Now, you all know that adjoint of S is that I told you in one class. So, this was is this, that you find out here that cofactor transpose of cofactor matrix, that you want to find out. Anyhow, we will see this. So, determinant of S is determinant of 40 minus 50 minus 50 100, this will be 40 into 100 minus 50 into minus 50. So, this will be 4000 minus 2500, which will be 1500. Okay. Now, you see the transpose of cofactor of S. So, S is 40 minus 50 minus 50 and 100. When you find out the cofactors for this particular element, you have to cross that particular row and column. So, ultimately what you get here, minus 1 to the power I equal to 1, j equal to 1. then what is remaining, that is 100. In the same manner you will go and you will find out here minus 1 to the power row 1 column 2, then what is remaining, if I go by this, remaining will be this, and here minus 1 2 plus 1, that remaining portion is this, and here minus 1 2 plus 2, remaining portion will be 40. The resultant quantity will be 100, then 50, then 50 and 40. Now, if you take the transpose, you will get the same thing, because it is a square symmetric matrix, you will get the same thing. So, S inverse will be 1 by 1500 into this. This will be your S inverse. Once you know S inverse, what you require to compute now, you want to compute now this one. So, I can see this one first. If I write S inverse x bar minus mu, then this is nothing but 1 by 1500 into 100, 50, 50, 40, and your x bar minus mu is 10 minus mu 1, 20 minus mu 2, 10 minus mu 1, 20 minus mu 2. So, 1 by 1500, this is 2 cross 2 matrix, 2 cross 1 matrix. So, your resultant will be 2 cross 1 matrix. So, 100 into 10 minus mu 1, 100 this into this plus this into this. So, plus 50 into 20 minus mu 2. Then again 50 into this 10 minus mu 1 plus 40 into 20 minus mu 2. So, this is our 2 cross 1. Now, you see T square, n equal to how much, n is 20, and x minus mu transpose will be 10 minus mu 1 and 20 minus mu 2, this will be 1 cross 2 matrix, then into 1 by 1500 into this total quantity 100, 10 minus mu 1 plus 50, 20 minus mu 2 by 50, 10 minus mu 1 plus 40, 20 minus mu 2, 40, 20 minus mu 2. Okay. So, this cut this one to 150, that is 75. So, if I write like this one, this is 1 by 75. Now, you see 1 is to 2 and 2 cross 1. So, you will be getting only one scalar value. So, multiply this into this and this into this. So, your resultant quantity will be 100 into 10 minus mu 1 into 10 minus mu 1, 10 minus mu 1 square, plus 50 into 10 minus mu 1 into 20 minus mu 2. So, this one multiplied with this totality. Then you will find out plus 20 minus mu 2 into 50 into this. So, I can write 50 into 10 minus mu 1, 10 minus mu 1 into 20 minus mu 2, plus you will get 40 into 20 minus mu 2 square. So, the total will be 1 by 75, 100, 10 minus mu 1 square plus 2 into 50 into 10 minus mu 1, 20 minus mu 2 plus 40, 20 minus mu 2 square. Okay. So, I said that this will be 1.33, second one is 1 point, again 1.33 it should be, 1.34 it is written, then this one is 0.53. So, resultant quantity is, if I divide this one by 75, that is 1.33, 10 minus mu 1 square plus 1.33 10 minus mu 1 into 20 minus mu 2 plus 0.53 20 minus mu 2 square. This type of equation you have seen earlier also. When I ask you to develop the bivariate constant density function, there you have developed this type of equation. It is similar, only difference is this one, and x bar is x, s will become sigma, and that was the issue there. Okay. Now, my second question is, what will be the distribution of it? So, distribution means t square follows n minus 1 into p divided by n minus p f p n minus p. That will be your distribution. So, n is 20 minus 1 into p is 2 divided by 20 minus 2, then f p is 2 and 20 minus 2. So, this will be 19 into 2 by 18 f 2 18. So, you can write 19 by 9 f 2 18. Okay. So, you see this slide again. So, our problem is this and your question is this and your answer is this. And in exam prime basically the 2 by 2 matrix will be given, but there is possibility also that you require to compute S given by maybe 3 by 2 matrix. Okay, this is 3 cross 2, this is the data matrix. So, instead of giving you straight away the S, what is required to be given? Required to be given because you will be getting this only. Initially when you collect data you will be getting this n cross p, and all other things are to be derived. Okay. This is what is Hotelling T square. What Hotelling T square give you? Hotelling T square gives you a confidence region. Confidence region CR. Okay. That means what we are trying to say, if we follow this one that t square equal to n x bar minus mu transpose S inverse x bar minus mu, okay, n into this, then we are saying that this is an equation of ellipse when p equal to 2. You have seen earlier when you have derived this something like this, then the equation this one t square equal to this is an equation of ellipse. So, 2 dimensional case it will be equation of ellipse, and you know what will be it in the multi-dimensional situation. What we want to say that this one is like this, the t square value is this will be less than equal to the required probability. What is the probability distribution here? Your probability distribution is this. So, if I say this quantity, so straight away if I write like this n minus 1 into p by n minus p f p n minus p, the totality I am writing that probability that this quantity will be less than this, what will be the value? If I put here alpha, 1 minus alpha. Okay. In 2 dimensional case depending on the alpha, so you will get a depending on, again it all depends on the covariance matrix also what type of ellipse it will be, but if the variables are independent then you will be getting ellipse like this. This is what is determined by this quantity. This quantity will determine this, and by 1 minus alpha, if alpha equal to 0.05, that means 95% of the observation will fall on or within the ellipse, on or within the ellipse. If you take alpha equal to 0.01, then your ellipse will be bigger. Reason, this contain 99% of the observations. This is known as confidence ellipse. This is known as confidence ellipse. Where from this ellipse is coming? That you have already seen that this is a quantity which an equation of ellipse when p equal to 2 and when p equal more than 2, it will be equation of ellipsoid. What will be the equation? What will be this equation when all the variables have equal variance? It will be a circle, and for p dimensional scale it will be a sphere. Okay. If all the variables have equal variance, ultimately you get a circle in 2 dimensional and a sphere in spheroid, I think that is the, that will be in the higher dimensional case. Now, we want to understand this confidence ellipse from the original variable point of view, like the x bar for the first variable, that is the mean for the first variable, and x 2 bar is the mean for the second variable. These are all sample mean. We can say okay fine, there are 95% observation within the ellipse or there are 99%, but how do we interpret this? Okay. One of the interpretation could be, suppose you find out the ellipse and then plot in the sense you fix all the points, suppose n points are there. So, you may get points are like this. Suppose you get some one point here, this is one point. So, if I consider the 95% confidence ellipse, then this is an outlier. So, this approach can be used for outlier detection also. Another important issue here is this, you see this figure, this is what we practice in quality control. What it says that there are 2 dimensions, that x 1 bar and x 2 bar, you see that individual confidence interval and the interval collectively is making one rectangular region A, B, C, D. So, that means some observation falling on here, suppose one observation falling here, based on individual interval it is within the confidence level. But collectively if you see that this is the collective confidence region, then this point is out of the confidence region. So, what is the interpretation then? Interpretation is, if your case is a multivariate case and you go by univariate analysis and accordingly you develop certain intervals, you may find out that the point you are talking about with respect to x 1 bar, this is within the interval, even within with reference to x 2 bar also this will be within the interval. But from their joint density, if we consider, this is not within the interval, in the sense within the region, confidence region. That is very important concept. That is why what is suggested that when you infer a multivariate population, you start using the multivariate characteristics of the population. You can go for univariate, but not fast. It is very clearly shown here that if I take this as a quality control example, then what I will find out? I will find out that if I go by univariate that control level UCL and LCL, then a point which is lying here, I will accept it as within control, but it is not within control. that will be reflected only when you go by the confidence ellipse in 2 dimensional case. In multidimensional case, confidence ellipsoid. The problem with this confidence ellipse is manifold. What is this? So, you are getting a region, but you cannot make decision based on this region. You only say that okay, it is outlier. Okay. For example, it may so happen that the point is here which is outlier or out of control. It is for which variable? Is it out of control for variable x1 or out of control for variable x2? You cannot make any comment based on this confidence interval. In confidence region, that confidence ellipse. Confidence ellipse or ellipsoid will give you idea that yes, one point which is out of the control from quality control point of view, but even other way from simple data analysis point of view you can say that it is an outlier. But why it is outlier, for which variable it is outlier? If you want to find out that, you have to transform from confidence region to confidence interval. What I am trying to say here now? I am telling you that yes, confidence region is the first step, you have to develop it. If you do not develop it, your inference will be faulty. Now, once you have confidence region, suppose one point observation is out of control or outlier, then what is required to be known, that which variable is responsible for this. Then you cannot do anything with this region, you have to go back to confidence interval for each of the variables. That is what is known as simultaneous confidence interval. I will discuss this, but before that I want to do little more on confidence region.